Well guys, I'm back. We're going to continue on with AC, and we're going to talk about inductors. This may probably take a couple videos, maybe even 3. There's a lot of information to go through, and so we'll try to make it through it as quickly as possible. I'm not going to go in depth, extreme depth with this, but we will go through it. First of all, what is an inductor? Well, simply put, that right there, hooked into a circuit, can be an inductor. Just a piece of wire. At ultra high frequencies, basically your inductors are nothing more than just either slightly curved or even possibly even a relatively straight piece of short wire. So let's look at this a little bit. First of all, let's talk about a little bit of terminology. Okay, these two will be like looking at the wire at the end, just a cross section of it. Now if I want to show current through the wire, I need direction. Well, if I put a dot, if the marker will work, well, fine, don't work. Try this one. If I show a dot, that means the current is coming out of the plane. Think of it like an arrow. If you got an arrow, then the part when the arrow shoots, the part that's headed towards the target or headed towards you would be the point, and it would just look like a point. If the arrow's going away from you, the wings on the end of the arrow will look like a cross. So when the current is going in, we just use a cross. And that just basically all that means is with the dot it's coming out, with the arrow or with the cross it's going in. Now, direction. If I hook up a piece of wire to a battery and get a current going through it, it's going to produce a magnetic field. Even in DC, you get a magnetic field. So we're going to use the right hand rule, and which means that we're going to be, in this case, talking the current flows from positive to negative. It matters not for all normal circumstances which way you determine whether you want to use conventional current, which is positive to negative, or you want to use electron flow, which is from negative to positive. The big difference would be if we're going to show which way the field is, which way the flux is moving, then if you're using electron flow, you have to use the left hand rule. But in this case, we'll use the right hand rule, which is conventional current. So if the current's coming out, we use the right hand rule. Our thumb shows the direction of the current, and our fingers will show the flux and the direction of it. So if the current was coming out the end of this wire, running like that, then my fingers will show the direction of the magnetic field. So in this case, using that, the field is rotating around like this. In this case, the current's going the opposite direction, so I turn my hand over with my thumb pointing down, and my fingers will show the direction, which will be like this. for all practical purposes, I'm not absolutely concerned about that direction per se. It becomes important when we deal with mutual inductance, but when we get to that point, I'll discuss that and how you can tell, and you won't really need to use any type of rules to know for sure if you have two coils and there's mutual inductance, whether they're adding, which means they're in phase, or they're subtracting, which means out of phase. Now, but the big thing I want you to understand is with a piece of wire hooked to any voltage source, DC in this case we're looking at, anytime there's current, there's a magnetic field. Now, a very smart man a long time ago actually wrote up a formula for this. It's called Faradays Law, and basically what he wrote up was what he determined was something like this, and you don't have to remember this, I'm just going to write it down. E for EMF, or induced voltage, will equal a minus D all this is a measurement of flux divided by dt. Now, it's a differential equation. That's what the D's are there for, but basically all that means is if I got a flux that is changing, in other words, this magnetic field that's actually changing with time, it's expanding and then contracting, but it's moving with time, then I get an induced voltage. So in other words, if I took that piece of wire, instead of hooking it up to a battery, I hooked it up to a voltmeter, and I had a magnet, and I started moving this wire in the field of that magnet, then the voltmeter would show a voltage. Now, the interesting thing is the negative here basically means, what that's telling you is the induced voltage is a counter EMF, what they call counter EMF. Basically, if my magnetic field is being produced from another wire that I put voltage on, when I move the second wire in that field, the actual direction of current will be in reverse to the initial wire. So if I had, say this wire, I've got it hooked to a battery, and it builds a magnetic field, but then I move this wire, or either one of the two, as long as I'm changing that magnetic field or moving a wire through that magnetic field, the voltage will be in reverse. That's what the negative means. It'll be in the opposite direction, just basically what it's showing here. So all that means, and that'll become important down the road, that it's counter EMF. Do not need to remember that formula by any means. It's Faraday's Law, and it just deals with the fact it starts beginning a connection and setting up a connection between electricity and magnetism. Now, there is another basic rule that deals with that, and that's called the left-hand rule. And basically, you set your hand in a position like this, and your thumb is the motion of the inductor. So the thumb will be how the inductor is moving, which can also be how, in reverse, how the magnetic field is moving. The direction of your finger will be this direction of the magnet, of the flux, and consequently your middle finger will then be the current, that the counter EMF that's induced into the wire. Now, the actual definition for inductor is inductance is, or an inductor resists change. When I hook up a piece of wire, first of all, to a battery, I don't get instantaneous full voltage and current. It takes a little time. To you and to me, it'll be instantaneous, but there is a certain amount of time it takes for the current to build up to full strength going through the wire. That allows the magnetic field will slowly build outward to that. While it's doing that, it actually is somewhat cutting the inductor. And when it does, it's trying to resist that change. So in other words, basically, as far as the inductor is concerned, if we start out with the battery not connected, there is no current flow, and that's the way it would like it. We hook it up to the battery, we get current flow. As that current builds up to a final maximum level, until then the magnetic field's trying to produce a counter EMF that's resisting this. The battery will win out, and we will get to full current pulling through the wire. At that point, everything's happy again. The field's not building anymore. It's not moving. So everybody's happy until we try to take the battery away. Then the magnetic field resists that again. The inductor does. So the definition of inductance is of an inductor is it resists change. And that becomes more important in AC. Now, if you take that wire and say coil it so that you get a wire like this, get a coil, and I ain't going to try drawing it in 3-dimension, then each one of those little fields that build around that wire will actually add up, and you'll end up with a bigger field. So if I start out with a straight piece of wire, it has a certain amount of inductance. Very small, but it's there. But then if I coil that up into a coil, such as like this, then all those fields, magnetic fields that was just around the wire itself, all start adding together. And I increase my inductance. Now the other thing, depending on the inductance will increase or decrease with respect to the number of turns. Another thing that will affect it is the diameter of the coil. How big around is it? And the length of the coil. How long is it? And then of course that's for air, but if I put a core in, a ferrite core, something made of iron, that will also, because what the core does is concentrate the magnetic field. So that brings us to some more math. Again, any of this can be found online. You can find calculators. So if you want to make up a coil and you want to, maybe you got a certain size of wire that you got, or you're looking for a certain inductance or whatever, you can go to a calculator online to figure out what you need, how many turns and so forth, the size of coil and everything else to get the amount of inductance you need. But inductance will always be an L. That's what we usually do. This will be in microhenries. Will equal R squared. R is the radius. times N squared, which is the number of turns. We divide that by 9 times R plus 10 L. Okay, this L is length, R is radius, this is in inches, and N's the number of turns. So if we look at a coil again, here what we're looking at is we take the diameter and divide it by 2 to get our radius. So that's our radius in inches. How many turns of wire that's here is N, and then the length, how long is this coil. Now some coils can be quite long, some can be a lot shorter. That is for an air core coil or inductor with a single layer of winding, like you would see in some of your older TRF radios. Their coils are generally wound as one single layer on the coil form. So that's what this is for. And air just means that there's no iron core in it. So again, L, or inductance in microhenries, equals the radius in inches squared times the number of turns squared divided by the sum of 9 times the radius, again in inches, plus 10 times the length in inches. And that for a single layer air core inductor will give you the inductance. If you want to know a multi-layer coil, then its formula is L, and henries, or yeah, microhenries, equals 0.8 radius squared in inches, number of turns squared, divided by 6 times the radius plus 9 times the length in inches plus 10 times the thickness. So in a case like this, we've got multiple layers. We would look at how thick that is as well, put in there. This is for air core as well. The formula for an iron core is a lot more drawn out, and it actually takes calculus to do it to get an accurate measurement, so I'm not even going to bother putting it up. Again, any one of these things can be found online as a calculator. Just look for inductor or inductance calculator and you can find it. Now, inductors with AC. Well, we're just going to throw some stuff out there about this. When you got AC on an inductor, AC is always changing. You got a sine wave, so the voltage is always changing. And now, unlike the battery where I get a relatively instantaneous current, the magnetic field builds and then it stays stable. In AC, my voltage is always varying. Now it starts from 0 at some point and goes to a certain level, peak a positive, then it starts falling back off until it crosses the 0 line, and then goes to some point maximum negative, and then back to 0. Well, now the inductor doesn't like this. we start off with zero, no magnetic field, but as we start building more positive, it has to build a magnetic field. And in the coil that's cutting, that magnetic field is expanding, cutting across all these wires and creating what is known as a counter EMF. Again, with the left-hand rule, it actually produces a voltage, induces into the wire that is in counter to the voltage that's applied, until it gets to a peak. Then there, everything's kind of stable for an instant. Magnetic field stable, the voltage being connected to it stable, but it won't stay there long, and it starts dropping again. So as it's building up, the counter EMF is opposing it going to this peak. Now, as it starts dropping off, the counter EMF will be opposing it from dropping off. It wants to keep that voltage at this peak. Eventually it gets to zero, and then we start going the opposite direction. Again, the field is fighting us. That's where you get what is known as the inductive reactance. X sub L, which is inductive reactance, equals 2 pi frequency times my inductor, my inductance. This is in ohms, just like X sub C, which is a capacity reactance. Both are in ohms. Its resistance basically to the change that that inductor is seeing to the AC. So frequency in hertz or cycles per second, inductance in henries. We increase the inductance, we increase inductive reactance. If we increase frequency, we increase inductive reactance. The biggest thing to understand is these are directly proportional to each other. So we end up with, well, let me draw something out here just to kind of. Another thing to remember about inductors is voltage and current. There is a phase difference. So from the old little saying, or whatever you want to call it, phenolic or whatever it is, Eli the Iceman. Well, Eli is for inductors. E is voltage, I is current, L is inductance. So Eli basically is telling you the voltage leads the current by 90 degrees in a pure inductive circuit. So the phase angle will be 90 degrees if it's purely inductive. Now the reason for that has to do with the fact that we do have the counter EMF. And the counter EMF is actually opposing change, which basically the current will not start picking up until we get to the peak. If we look at our voltage, as we start applying our AC to the inductor, we won't really see the counter EMF is almost perfectly opposing all the way up until we get to about the peak right here at 90 degrees, and this is when you'll start seeing the current flow, and it'll be 90 degrees out of phase. It'll cross at about 90, it should cross at 90 degrees and come back down. It will be less than the voltage because of the inductive reactance. So the current don't start until we hit that peak, and then we start showing current. As it will peak out pretty much right at 0 applied voltage, right in here, mainly because as we start going this way, the counter EMF opposes the voltage that's applied dropping, so it's building up that current from the counter EMF. Once this applied AC hits 0, we hit maximum peak of our current in the coil. Oh, how are we doing on time? 26 minutes. Okay. So, that brings us to phase, angle, and vectors. The standard when we draw it out in a phase angle type relationship, we're using vectors. This being 0. Across the bottom is the current in the coil. Along this line is the voltage in the coil. Now, in a pure inductive circuit, this is what you get. You get a perfect 90 degrees, but an inductor is not perfect. So, inductors have resistance. If I measured this with an ohm meter, there's a certain amount of resistance to this wire. So if I take these two leads out and hook them to the ohm meter, it's going to read a certain resistance in here. So we have to deal with, for sure, impedance with the inductor. So impedance, Z, in ohms, will equal just the square root of my resistance squared plus my inductive reactance squared. Gives me my impedance. So it's just a right triangle basic formula, but it's actually something like this. This would be your impedance across there. Now we'll deal with this more when I get into full AC, dealing with when we have inductors and resistance and in a circuit as well as capacitance. When we start working in that, we'll start really going deep into that impedance formula. So at this point, I think I'm going to cut this off at this point. In the next, we'll maybe be able to get a little further along, and in the next video we'll probably go into mutual inductance, because I kind of want to spend a little bit of time there. Well, not much, but just a little bit. And then we'll go into inductors in series and parallel, how they're figured. Then we'll go back to this impedance and phase angle a little bit, and then we'll talk about transformers. So at this point we'll stop the video here. We'll call this part 1 of inductors, and then I'll move into in part 2 we'll try to cover hopefully the rest of it. Part 2 might be just a tad bit longer. If I don't get all the way through it, then part 3 will absolutely cover transformers in a general sense, and and then we'll move into full-fledged AC. So I want to thank you for watching. If you like theory videos as well as restoration videos and everything, and you're new to my channel, you know, give a thumbs up on this video and subscribe. That way you'll be informed when I put out a new video. You guys can also go back and look through my old videos. I'm planning on doing a video. It's a repeat, but I decided that it may not be a bad idea sometimes to repeat certain things I've done a long time ago on schematics, reading them as well as locating components that's on the schematic versus where it's at in, say, a radio. I think that's kind of an important topic, so I'll be doing a video here here before long on that, so look forward to that as well. So anyway, I want to thank my new subscribers who have recently subscribed, and thank you for your comments. I tried to get back to some of them anyway, so you know, keep on watching, and again, if you like the video, give a thumbs up, and I'll see you guys on the next video. Thanks for watching.